Hi everyone, my name is Abraham and I'm a PhD student at the University of British Columbia in Vancouver, Canada. Today I'll be presenting our paper Understanding the Resilience of Neural Network Ensembles Against Faulty Training Data. This work was done with my colleagues under the supervision of Professor Karthik Pattabiraman and Professor Sathish Gopalakrishnan. When an autonomous vehicle encounters a road sign, it can usually rely on its underlying ML model, probably a neural network, to determine the type of road sign. Neural networks like these are typically trained with large amounts of training data. This makes the ML model's behavior entirely training data driven. We often hope that the training data is well curated. That is, the training data is correctly labeled and is complete. Shown here is a snippet of a dataset that could be used to train an autonomous vehicle in road sign detection. In this case, images of road signs correspond correctly to their respective labels. We train a common neural network architecture on the German road sign dataset, GTSRB, which is a well-curated dataset. The neural network predicts this observed image of a road sign as a speed limit of 70 km per hour. Since large amounts of training data are required, ML developers often resort to crowdsourced data, or use other ML models to automatically generate labels for training data. However, these options are error-prone, and may result in lower quality data. It is also expensive and often impossible to manually verify all the training data in large datasets. In fact, studies have shown that even well-used public datasets, like ImageNet, have 6% of their training data mislabeled. And in a popular open dataset for training self-driving cars, 33% of the images were found to be either mislabeled or were missing labels altogether. These are worrying discoveries, since faulty training data appears to be quite prevalent. Let's look at an example of one type of training data fault. Here, the training data is mislabeled, where incorrect labels are assigned to images. When the same neural network is trained on the GTSRB dataset that is injected with 30% randomly mislabeled data, the road sign image is misclassified as an alert sign for a road bend to the right. This could lead the autonomous vehicle to dangerously veer to the right, causing injury. So, what can we do about this? Well, we know from traditional software engineering that software reliability can benefit from end-version programming, where different versions of the same program are executed and combined through majority voting. End-version programming has long been used in critical control systems like in airplanes. End-version programming relies on the fact that because each version is developed independently, their algorithmic differences will lead the versions to behave differently in the presence of bugs. Inspired by end-version programming, could we instead have multiple ML models of different architectures perform inference, and combine those results through simple majority voting? The setup shown here is a form of ensemble learning. Ensemble learning has been used for boosting classification accuracy. We hypothesize that ensembles tolerate training data faults by outvoting misclassifications. But we're not only interested in correct classifications. What happens when the ensemble succumbs to training data faults? Will each model misclassify uniquely in their own way? Or will they all mistakenly agree on a misclassification? This is the least desired outcome for any ensemble. Our analysis aims to understand how to build ensembles that maximizes correct classification while minimizing cases like these. Therefore, our contribution is to answer the question, can ML ensembles tolerate faults in the training data? And if so, how? Fortunately, the answer is yes. We find that ensembles do offer resilience against faulty training data. Additionally, we observe that models in the ensemble are likely to disagree on misclassifications. Now we will begin to explain our experimental process. For our experiments, we build an ensemble of 7 architecturally diverse ML models, which we refer to as NN Ensemble. We inject 3 types of trained data faults at varying amounts across 3 standard datasets. These datasets include MNIST for handwritten digits, CFAR10 for objects, and GTSRB for road signs. We built NN Ensemble with 7 neural networks, choosing neural networks with varying architectures and depth, from shallow to deep. For example, a recurrent neural network works very differently from a ResNet 50, which has residual layers. The architectural diversity allows each model to focus on different parts of the input feature space, and thus behave uniquely in the presence of training data faults. In addition to mislabeling, we also consider other types of training data faults, such as removal, where training data is accidentally deleted, and repetition, where the same record is duplicated in a dataset. Together, these represent a set of common mistakes that are unfortunately prevalent in many training datasets. As part of this work, we developed our own tool called TensorFlow Data Mutator, or TFDM for short, to systematically inject faults into the training data using TensorFlow 2 APIs. TFDM supports many different fault types, beyond those that are presented in this paper, and is available on GitHub. I encourage you to check it out. Our experiments aim to answer the following questions. Are ensembles more resilient than individual models? Here, resilience means resilience to training data faults. And if so, what characteristics of ensembles make them resilient? And finally, how do we characterize misclassifications caused by faulty training data? To measure a ML model's reliability against training data faults, we devised a metric which we call the accuracy delta, or AD for short. We first train a model without faults, we call this the golden model, and remove the test images that it misclassifies. We then train the same model again, this time with faulty data. The accuracy delta is then given by the proportion of the filtered test images that are misclassified by the faulty model. In this case, it is 67%, or 2/3. Since ML models are inherently approximations, even the best ML models will misclassify on certain inputs. They're rarely 100% accurate. We remove data that has been misclassified by the golden model to focus specifically on the effect of the injected training data faults, without double counting. Here we show a graph plotting the accuracy delta for each individual model trained on the CFAR10 dataset, injected with 30% random mislabeled faults. On the x-axis are the individual neural networks, and the y-axis is the accuracy delta. The lower the accuracy delta, the more resilient the model. On the far right of the graphs, we show the accuracy delta of the ensembles. We observe that the ensemble has a lower accuracy delta, hence is more resilient than any other individual model. We also observe that models with greater classification accuracy when trained with well-curated data are not necessarily more resilient to faulty training data. For instance, in CFAR10, ResNet 50 had the highest golden accuracy of all individual models, but it did not have the lowest accuracy delta. That would be VGG3 in this case. Now let's move to the second research question. Each row in this figure represents a test image, and each column represents the classification result of an individual model within an ensemble. Check marks indicate correct classification, and crosses indicate misclassifications. We introduce a diversity metric called the Gini coefficient, which is well used in economics to compare income inequality among countries. We use the Gini coefficient to measure the distribution of ensemble classifications over test images. The Gini coefficient is a value between 0 and 1. When it is equal to 1, then individual models work better than an ensemble. If it is 0, then the ensemble is unstable. A value in between, like 0.5, could indicate that the models agree just enough to achieve correct classifications under faulty conditions. Now, the Gini coefficient has been used in other aspects of machine learning, but we are the first to use it for machine learning reliability. As a naive example, if models 1, 4, and 5 always correctly classify all test images, while models 2 and 3 are incorrect, the Gini coefficient would be close to 1. You see here, the ensemble isn't very useful. We could just use one of models 1, 4, or 5 instead. On the other hand, if all classification combinations are unique across the test images, the Gini coefficient would be close to 0. And since the ensemble is not very stable during inference, the ensemble could actually be less resilient than the individual models. We show the percentage of test images that are correctly classified by the number of individual models in the ensemble. In this example, we do this for varying amounts of mislabeled data along the y-axis for the CIFAR-10 and GTSRB datasets. The red trend line marks the majority boundary, where the part of the graph to its right is where the majority of models classifies correctly. As you can see, as the percentage of mislabeling increase, it becomes increasingly difficult for the ensemble to tolerate faults. The ensemble is able to classify correctly at least up to 50% faults. CIFAR-10 has a Gini coefficient of 0.774, which is lower than GTSRB, which has a Gini coefficient of 0.894. This means that the use of an ensemble for CIFAR-10 has a much higher impact on resilience than for GTSRB. For the last star Q, we dig deeper to find out whether ensemble resilience differs by label class. We show an example of our findings for CIFAR-10. CIFAR-10 has only 10 label classes, so we show them all here. On the left is an ensemble trained without faults. The lighter the shade, the more models in the ensemble that are able to correctly classify images of that label class. Again, the red trend line is the majority boundary. Similar to how we measured the accuracy delta, we remove all the misclassified cases by the golden model. When the ensemble is trained with 30% data removed, notice that the cat images are disproportionately impacted compared to other label classes. We find that cat images are much more likely to be confused with other animals than other objects like a truck. This analysis shows that label-specific measures can be taken to further improve resilience. In this case, perhaps just add more differentiating examples between cats and dogs. In the future, we will look at more efficient ways of generating diversity, as well as trying to understand the effectiveness of ensembles on other real-life critical systems like medical diagnosis. In summary, the problem that we encountered is that ML models are often trained with faulty training data. We evaluate ML model resilience by systematically injecting artificial faults into the training data, and reason about their resilience using our own diversity metrics. We find that ensembles are more resilient than any individual models, and that correct classifications are usually reached with high consensus. And an ensemble is available on GitHub, and you may learn more about our work at this link. Thank you for attending this talk.